There'll be 2 parts in this lecture, which means 1 hour and then 1 hour. And I will make a natural break in the middle. Okay, the first part will be about our pure category. I mean, so I will speak about Morita equivalence and Tannakian category, so it will be pure category. The second part will be connected with multi-zeta and geometry. And for the second part, I recommend a very good exposition which was given by Deligne a year ago in the Bourbaki seminar, where he reported about the work of Francis. And the first part of his lecture was a very good account of his own work and his work with Goncharov. And I think, to me, is the best explanation of his work, and it's palatable. Okay. So I will use, for the second part, I will use his report. For the first part, I will, where is it? I will first speak about Morita equivalence. Which is something, I think the paper of Morita is 1953, something like that. And Morita was motivated by finite group theory. When you have 2 different groups and a finite group and a prime number p, you can speak of the block associated to p for one group and the block associated for p to another group. And it may be that even if the group G and G prime are quite different, for a given p, the blocks look very similar. And that was the idea. So, well, you can say that the block associated to a group are certain, can be considered as a module over a certain algebra in characteristic P, which depend from the group. Okay, so, and of course you can transfer information from one group to the other one, and I refer you to the Atlas famous book, compendium containing most information about finite groups, and it was very used in that. So more generally, Morita equivalence is about comparing 2 categories of modules. So suppose I have 2 commutative rings, non-commutative, important non-commutative rings A and B. I want to compare the category mod A with the category mod B. My notation is that A acts on the left, and you similarly for the right action. So I want to have an equivalence of these 2 categories. How to obtain this? Well, the recipe is quite simple. Take A, B, the ring A considered as a module to the left over by itself, acting on itself by the left. Then suppose that you have suppose you have a functor mod A T to mod B, to B mod, A mod to B mod. And then you apply T to this, well, T to A considered as a left module over itself, sorry. And then you get a B module. You get a B module, which I will call P. But P will be a B module. But on the other hand, on A considered as a left module over itself, there is an action of A by the right multiplication. Since T is a functor, this action by A on the right transfer to this, which means that what you get is a bimodule. PBA is a bimodule. B on the left, A on the right. Okay. Now, you have one property that AA considered as an A module has 2 properties. First of all, it's projective and finite type. Okay. And then finitely generated. Second, it's a generator. What does it mean, a generator? It means that in order to generate any A module, you take a families of copies of A, a direct sum of a family of copies of A, so A to some power AI, and you divide it by some relation, and you get P. You get any module, I'm sorry. Any module is a quotient of a free module. That's what I'm saying. So, since this property Well, there are many ways to formulate this. Since this property is really intrinsic with respect to the category A mod, the equivalence transfer it to this. So PBA is projective as a B module, and therefore it generator as a B module. Any B module can be obtained by taking direct sum of a number of copies of P and taking a quotient. Okay. Furthermore, if you look at the endomorphism of AA as A module, it's okay. What commutes with the left multiplication are the right multiplication, so it's A. And therefore, because we have an equivalence of category, what the third property is that A should be isomorphic to the endomorphism over B of PBA.
So for this property, you don't need any constraint on T?
No. Well, an equivalence. While an equivalence. I'm just saying that T is an equivalence of these two categories. So the endomorphisms here are transferred to the endomorphism there. So that is true. So P, once you have an equivalence of category of module, you generate a bimodule P, BA, which has these three properties. And the functor itself can be recovered. As follows. If you have an A module M, which is in this category, the image in B is obtained by the tensor product, where you can imagine P, B, A, tensor A, M. Obviously, I mean that I take the tensor product over a left and a right module over A. So that's the fourth property. Now, Morita statement is converse to this statement. It is the following. If you start with a bimodule, over A and B, which has these properties, as a B module, it's projective of finite. It's a generator of the category of B modules. And second, when you have a bimodule P over A and B, B acts as endomorphism of A module, A acts as endomorphism of B modules, and you have exactly that. And conversely, it can be shown that, B is also isomorphic to the endomorphism over A of AP. So, and then if you have this property, if you have a bimodule which has these properties, and if you define a functor on the A module by this tensor product, then it's an equivalence of the A module with the B modules. That's Morita equivalence. Now, in the work I did long ago about algebraic groups in characteristic P, I refined the result by Dieudonné, and the full exposition is in the textbook by Gabriel and de Mazur and Gabriel, which can be formulated in the following way. The point is that we will not compare two categories of module, but a certain category is a category of modules. And that's the interface. So the category of group will be the following. I will take a field K perfect of characteristic P. And I will take the category G, which is a category of pro-unipotent group scheme over K. Or if you want, a group is viewed as an inverse limit of group Gn, where each Gn is a matrix group which is unipotent. That means Gn can be realized as a subgroup of the matrices of this type. As an algebraic group is a subgroup of these matrices. The triangular matrices is one on the diagonal. And so each Gn is such a group, isomorphic to such a group, and you take an inverse limit. That's an element in the category G. And we want to have a description of the category of this group. Well, in characteristic 0, such group have a Lie algebra and first of all, in finite dimension, and then by limit, what you have is that for such a group, you have the Lie algebra, which has to be taken in the sense of equivalence. For if the group is infinite dimensional, it's an inverse limit. If you have a group G, which is the inverse limit of the Gn, the Lie algebra should be the inverse limit of the Lie algebra. That's something that Quillen told us. So G, now there's an exponential map from G to G, which is obtained first of all in finite dimension and going to the limit, exponential map. And as a scheme or algebraic variety, the exponential is an isomorphism in characteristic 0, which all you have to show is that for this group of triangular matrices, the exponential is, the corresponding Lie algebra is obtained as follows, and the exponential of a matrix of this type to a matrix of this type is a one-to-one, it's a one-to-one transformation, which is rational, and with inverse, which is rational. And the point is that if you take a subgroup here, there will be a corresponding Lie algebra, which is a vector space there, and the exponential brings the Lie algebra onto the group, and that's easy to go to the limit. So in characteristic 0, it's easy to characterize this group. They are defined by their Lie algebra, and the Lie algebra is the same as is a nice inverse limit, a category of inverse limit of Lie algebra Gn. Gn being nilpotent, which is the same, nilpotent in the sense of Lie algebra, which is the same, can be embedded into this Lie algebra. So here you have a complete understanding of the category, provided you know how to classify nilpotent Lie algebra, which is not so easy. But okay, in characteristic P, we don't have any exponential, of course. But what we have is that we can, for such a group, we can define the group of curves. Well, the best way to define it is to say that I'm taking the group scheme and the point in the ring of formal power series in one variable. And well, all my schemes are fine schemes. So it's easy to define what I mean by. In general, what I mean by a point over a ring. So my scheme is over K. So any commutative K algebra produces point. And since G is a group scheme, this is a group. So I define this group. For instance, in the case of a matrix group, it just means that you have a power series of matrix, depending on the parameter T, power series of matrix, which for each value of T is in the group. So that's what you have. Now, on this, you have special operations. First of all, you have VL for L is a prime, which applied to a curve gamma just mean replacing T by T to the L. Or if you want to act on this ring by some endomorphism, you transfer it to the group. Now FL, the corresponding Frobenius, so that's a Verschiebung in German, décalage or translation. F is for Frobenius. Well, this notation came from Harty and Hasse in the 1930s. Just like generalization, F gamma of T is obtained as follows. You take zeta, which is a primitive L root of unit. You are joined into the field, and you take the sum for I0 to L minus 1 of gamma of zeta IT, and here it depends only on T power L. Well, as long as this is valid for any prime easily, here L equal P makes a difference. Of course, you have no P root of unit in characteristic P. What you do, you work formally. In order to define a P's root of unity, so zeta L, let's say, in order to define zeta P, you just do generically, take a root of this equation, you take a generic root of this, that means you take the quotient of a polynomial ring like something, you take a generic root and you repeat, and it works. So, now, okay. Now, what you need here is to consider what I call P-typical curves. A curve F is, if it satisfies the property that FL of gamma is 0 for all L prime different from P, P-typical. The idea is that if you could lift in characteristic 0, then a gamma of t would be the exponential of something, c1t plus c2t2 plus etc. And when you have this, you act by this, it just means that the only power of t which enter are t, tp, tp squared, etc. Well, it doesn't make sense, except that the Hasse-Witt exponential is the following, is exponential of t plus tp over p plus tp squared over p squared, etc. Oh miracle, no p in the denominator when you expand it as a power series of t. Then you take this exponential, which is highly singular for p. Well, this is highly singular for p. Take the exponential, it's regular for p. You can reduce it mod p, which is quite a miracle, but it's the two. So now this is the idea. If you can lift everything to characteristic 0, it means exactly that you have this, and so you have only C1 TP, C2 TP squared, etc. Okay, now this P-typical curve, the point is that to each group you associate the module Jude. Well, Jude is a joke. Judon, when he was in the United States, was often called Judon. Judon was translated by some Americans as Judon. he was fond of this joke. So Jude of G is the set of all typical curves. All typical curves. Now, what you have in that, these are part of the curve, but you add a lot of operators, F, VL, FL, they almost all disappear. Well, VL is of no importance, and what remains is FP and VP. Also, you have the scaling operators. Scaling operators is defined as follows. A gamma is just scaling the variable. You replace t by AT, and that's it. So the Giordani module is a certain commutative ring which has operators of the type FP, VP, and A satisfying certain relation. And this relation defines a certain ring which I will call Jude of over K. Well, maybe it's, I would call it, well, no name. Let's call it D over K, depending on the field K. K, yeah, depending on the field K. It's a certain algebra. It's a certain ring, not an algebra over K. Okay, but now what you have is that if you consider this category in the over a field of characteristic P of this pro-unipotent group scheme, you apply to this factor, which take a group to a certain, well, I will call it the category of Giordani mod. So a ring with a group with some operators, which is a module over a mod. Well, I would say it's better dk mod, and you have the functor which goes from G to dk mod, and you show that it's an equivalence of category. So it's not an equivalence between two categories of rings, two categories of modules of the rings. It's a certain abstract category which is made equivalent to a category of modules. And from that, of course, you gain a lot of information about your group. This is really the substitute for the Lie algebra. So it's much more characteristic P, it's much more complicated than an ordinary Lie algebra. But then, of course, for people who have not yet studied operads in characteristic P, it's time to do it. Okay, it's okay. But you will be, they will be full of surprises, full of surprises, just to show you what flavor, the flavor of this. Okay. Now, how do you do that? How do you prove the equivalence? By analogy with what I stated about Morita equivalence. Well, you introduce a certain group scheme, which I call W for width, P infinity, meaning the following. It depends on the prime P, but there are digit vectors of infinite lengths. Okay, VP1 should be the width vectors in one of length 1, VP2 of length 2, and so on. VP, it's an algebraic, it's a group scheme in the category, what was the name for this category? G? No, there is no name. Oh, yes, in the category G. And what you can show is that it represents a functor. That means dude of G is isomorphic to the homomorphism in the category G of W P infinity to G. Well, Dieudonné had a different presentation. He did not recognize at first the width vectors. He introduced a certain group scheme. Well, this is basically due to Dieudonné, but he did not mention the width vectors. And that was my part to generalize the width to mention that it was the width vectors and to make the connection and to generalize it. Okay. So this functor is representable. Now the fact this functor is an equivalence of category, so in particular it's exact. What does it mean in a category that this functor is exact? It just means that this is projective in the category. Okay. So here WP infinity is a projective object. WP infinity is projective in the category G. Second, the functor is faithful. It's faithful. Well, a part of an equivalence is that it is exact and faithful. The fact that it is exact, faithful just means that VP infinity is a generator. Well, that the functor is exact from my description, which is not the description of Dieudonné, it's immediate that the functor is exact. So, the only thing which is not trivial is to show that WP infinity is a generator, which means that every such group in this category of algebraic group is a quotient of a direct sum of copies of this WP infinity with vectors. Well, if you want to deal only with, well, all my groups are pro-algebraic groups, that means inverse limit of finite dimensional algebraic group. You can restrict yourself to this group and then go to the limit. It's easy. So the only point is that, the only point is that you have to show, you have to show the generator. That means you have to show that any group unipotent, the basic fact is that if you have any algebraic group of this type in characteristic P, it's a quotient of a finite sum of truncated width vector, because WP infinity is per definition inverse limit of a group which are of finite dimension. This dimension is n or n plus 1 depending on the convention. So what you have to show is that any unipotent group in characteristic P is a quotient of, I'm sorry, this group should be commutative. I'm sorry. At this point, I forgot to say. Well, here in characteristic 0, we can have groups which are non-commutative. Now I restrict myself to commutative group. In characteristic 0, the Lie algebra is nothing, just a vector space. The bracket is 0. I'm sorry. so far we don't know how to, we don't know how to generalize this to non-commutative group. The statement of Dieudonné and myself is restricted to commutative group. I should say that. Okay. Otherwise, let's say simply the multiplication of curve should not be commutative if the group is not commutative. And so, well, I have to, well, where to put it? Now G commutative. So you have a group, a category of commutative groups, and this category is isomorphic to a category of module over a certain range. That's a point. Now all you have to show is that now in finite dimension, you have to show that this G is unipotent and commutative. Sorry for omitting that before, commutative. Then it's isomorphic to a quotient of V of, let's say, Vpn to some power R divided by RH. Well, of course, the Witt group is a commutative group, so you cannot expect to control non-commutative groups. Sorry for that. So that's it. But you see, it's a typical instance where you compare a category, a certain abstract category, with a category of modules. And Morita equivalence is a generalization, generalizes to this. And you can easily formulate an abstract statement which says that if you have a functor from an abstract additive category to a category of module, when it is an equivalence. Very similar, exactly that. If you have replaced here replace here A mod by C, and then you have exactly, you have an equivalence of category. It's exactly the same. But now I'm interested not in modules over algebra, but of co-modules over co-algebra. You will see why. You will see why. When you have an algebraic group, an affine algebraic group, the functions, so as an algebraic variety or scheme, it's a spectrum of some commutative ring, the functions on the group. Now, so you have you have an algebra, but the group law corresponds to a co-product in the algebra of functions on the group, obviously. And now, so in order to define an algebraic group, we have to have a product and a co-product, a Hopf algebra, as it is well known. I don't have to repeat it. But I prefer to begin with a co-product first, and then to have the product. You will see why when in the application, the second part. So now I'm interested in a certain problem, which is, suppose I have a certain category C, which is, I suppose, K linear over some field, K linear. But the characteristic may be 0 or non-zero. Doesn't matter. It's irrelevant. So category, K linear category at first. And I define by vect the category of vector spaces over K, and vect exponent F, the finite dimensional vector spaces over the same field. And, well, the point which we'll use at some point, at some instant, is that knowing the category of finite dimensional vector spaces, you can reconstruct the category of all vector spaces by taking inductive limit, direct limit, and how to extend a given additive category to have the direct limit or inverse limit. It's well known, and Grothendieck did it, and it's well known. I don't have to repeat. It's advantageous to do that. Now I will consider a functor from an additive functor from the category C to the finite dimensional vector spaces. Now I'm interested not in modules but in co-modules and co-algebras. So if C is a co-algebra over K, there is an easy lemma which we have to prove at the very beginning, which is the following. if you start with V, any vector space which is finite dimensional, for all such V, there exists a C prime in C, which is a sub-coalgebra, with the two properties that it contains V and it's finite dimensional. So any coalgebra is a limit, a direct limit of finite dimensional coalgebra. No such things exist for rings, of course, or algebra. That's the main point. Now, if I consider comodules over C, and I will usually put comodule over C upstairs. A comodule, where it's given by a map, which is call it M, by a map which maps M into C tensor M, the coaction. The tensor products are always overkill. The coaction. Again, a very similar statement is valid, is that if M can be represented as the union, filtered union of M alpha, such that M alpha by the coproduct maps into M alpha tensors. Tensor C alpha, there is M alpha and C is similarly a limit of C beta, let's say C beta. And the point is that if you have any finite set or finitely generated subvector space into a comodule, it's embedded into a finite dimensional, which is a comodule, a finite dimensional comodule over a finite dimensional coalgebra. That's the point. So in a sense, things are almost finite dimensional, and if I stated that the vector spaces can be recovered from the finite dimensional one by well-known process in category theory, that's because I have this in mind. No such thing is valid for modules over rings, of course. And this detour by a coalgebra could be translated in the framework of algebra by introducing algebra with a linear topology, etc., complete linear topology. But it's just part of a standard duality that the dual of a vector space, whether finite dimensional or not, is a topological vector space. There's a natural topology on the dual of a vector space, the field being taken as discrete, and conversely, the original vector space, the discrete vector space, is a continuous dual of its dual. But, well, in Jordan it's usually, and Gabriel it's usually stated in this form, but it's better to consider a coalgebra. Okay, so now we have this, and we are interested in such functors from an additive K-linear category to the category of vector spaces. Now what I will show you, well, at least sketch a proof, that in such a case, for given T, given C and T, there exists a coalgebra we'll call it C sub T, and a factorization of the functor from C to C T comodules of, and I put an index F, vector space of finite dimensional F. This means the comodule over Ct, which are finite dimensional over the base ring. And so, my functor T will be factorized through such a functor with the property that this is a forgetful functor. Any comodule is a vector space, and you forget about the coproduct, and you have the forgetful functor. So, and uniqueness is easy to state. So, any such functor can be factored through such. You go first to comodule, and then you forget the coaction. The point is that we can give an explicit construction of the coalgebra. Well, first of all, if V is a vector space, in the category vector Ft, there is a corresponding coalgebra C of V, which is obtained as follows. You take the endomorphism ring of V, the metric ring, it's a finite dimensional algebra, you take the dual. As you know, the dual of a coalgebra is always an algebra, but in order to get good control of the dual of an algebra, you need finite dimensionality. So here it's finite dimensional, so it's a dual and V dual. I use this for the dual. Or you can represent it as, let me see which way. CV is V tensor, dual tensor V. And N on V is naturally isomorphic to V tensor V dual. This is, I use the Dirac notation brackets if you want. Okay, so these are the bras, these are the bras, these are the cats. Okay, so it's a dual of an algebra, I don't have to explain. So I have this one. And then that's the first construction. Now I will construct the coalgebra corresponding to this functor, and that's the crucial ingredient, and I think the main message today. The main message today. How do? I take the collection X runs over the object of C. For each such X, I consider T of X, that's a vector space, and the corresponding coalgebra. So, of course, what you have is that you have a natural map from V to CV tensor V. No, to the opposite. V tensor CV, to it, co-module to the right, and which is just expressed that V is a module over endomorphism of V, so it's a co-module over the dual of this algebra. Okay, so now you take C of T of X. Now you take the direct sum over all objects of C. Now I see the ghost of Buradi 40, the ghost of Russell planning around. What do you mean by the sum? Well, assume that in your category, to be safe, there is a set of objects such that a set, every object is isomorphic to one in the set, so a family. Well, I don't want to enter into the universe and things like that. Okay. In practice, it's satisfied. So it's not difficult to show. I take this. This is a direct sum of coalgebras. This is a direct sum of coalgebras. So this is, well, preliminary form, gamma T, it's a coalgebra. You know the notion of products of algebra, by duality, direct sum of coalgebra. Okay, so gamma T is not yet there. You have to introduce some relation. And the relations are obtained as follows. I will define some other space, HT, and two maps of HT into gamma T, two linear map, and I will take the co-equalizer of these pairs of maps. Or if you want, I will introduce the difference of the linear maps and the co-kernel. So I have to construct such a diagram. Now, H of T will be obtained, H of T, yes. How to define H of T? That's the point. Well, gamma T is a direct sum over the X. X is an object of CTX. Now, H will be a double sum. H of T will be a double sum over X and Y of something. What is this something? This something is the following. I take two objects, so let's say, provisional notation, ht of x and y. So I have to define ht of x and y for two objects. How do I do that? I use the following. T of x and t of y are vector spaces. Now, in the category C, well, maybe C of xy, the homomorphism in the category C form another vector space, finite dimensional. Well, I assume it is finite dimensional. Well, it's not really important. Assume it's finite dimensional. So, in my category, the Om from one object to another one form a finite dimensional vector space. Now, I take the tensor product, and I will have two maps, one over y, over ty, one over tx. And by taking a direct sum, I will obtain the two maps from H to gamma. The first arrow will give me, by taking direct sum over x or y, will give me one of the maps and the other one. Now, what do you have? This is as follows. The fact, no, it would be better to say yx. The fact that x is a functor means what? That if you omit this part, the homomorphism in the category C from x to y act transforming the vector space Tx into Ty. That's the description of the factor. Now, sorry, I should put here the joule. And 2 Tx joule, that's it. Now, by transposition, if C, a morphism here in Cxy from x to y gives a map here, by duality it gives a map there. Over with the same, yes, over the same. Maps Tx into Ty by duality there. So you have this, and you tensor by Tx. So it goes. Let me see. Where does it go? It goes to the old. Oh no. Okay. Now, this goes to Ty, but by tensoring, you go to C of y. I'm sorry, to C of y. You had these arrows which go to Ty. You tensor it by Ty dual. That's it. C of y. Sorry. Similarly, you go here to C of x. That's what we wanted. C of Tx and C of Ty. That's right. That's the diagram. I'm always trouble with this diagram. So you have these two maps. And I take this as, by definition, ht of xy. So I have two maps, ht of xy to Ctx and Cty. And that I combine them by direct sum. I got this. And I take the co-kernel of this double arrow. That's, by definition, the co-kernel is the co-algebra I want. Of course, in order to get that, I started from the standard definition of algebra, the algebra of endomorphism of a factor into itself, and I dualize everything. This is just it. But it's important to see that you have two different things. Here you have T of x and T of y. Here you have the homomorphism in the category C. Okay, so that's the way. Now, once you have that, it's a simple exercise to show this factorization and that it is universal. Now, the point is that in reality, what you can do is to represent, let's say, yes. The direct sum of the Cx, CT receives V star V dual to V, and which is the following. If I take any element V in V, in T of V, I'm sorry. Yes, well, if I take an element V in V and an element in the dual V star, I represent by V dual the corresponding element in the coalgebra. V star. So in the coalgebra. So what you have here is the following. You can define your coalgebra by generator and relations, linear generators and relations. I'm just translating, it's a quotient of a direct sum, and every element in the direct sum is a tensor product. So what you have is that you have symbols from the following fact, In order to define C, it's generated by symbol. I will call them omega and gamma, for instance, or C. C will be an element in TV, some TV. Omega will be a linear form on TV. Yes. And these are generators, linear generators. So, all these. What are the relations? I translate this relation, and they are obtained as follows. Omega of TF V is the same as omega TF V. Why? TF acts on vector. It's a left action. The transposition, instead of writing transpose, I let it operate on the right. So this is the rule. So my generators in the coalgebra are characterized by pairs of an element in some vector space and an element of vector dual, and the basic relation. I started from this and I reformulated it this way. Okay, that's it. You will see applications. This is the formal integral of f of omega into domain V. That's a formal integral. That's what I had in mind, of course. So that's it. So I know this coalgebra, this factorization. Now I need something more. When can I assert that the first factor is an equivalence? From the given factor with very little properties, I construct the comodule, the coalgebra and the comodule. When is it that Z is an equivalence of categories? That's the crucial point, of course. You want to compare an abstractly given category to a category of comodules. Now, I give you the result. The proof is routine. Theorem. Call this functor, let's say omega t, or omega t, it depends on t. Omega t from C to comodules finite rank over the coalgebra CT.
Sorry, the notation omega has nothing to do with omega.
Oh, I'm sorry, no, wait. No, it's not the same. Call it lambda if you want. Any calculator. No, it's not the same. Lambda. Thank you. Lambda of t, so I've defined this factor. When it is so, is an equivalence if t is exact, t is faithful, but I know how to make some assumptions on C. C is an abelian category now. Abelian category with finite dimensional ohms. So far I did not use that. C was just a K-linear category. So it's an abelian category over K, abelian category, finite dimensional ohms. This factor is well defined, starting from T, I construct this. And this is an equivalence if this two property odd is exact. Exact means that an exact sequence in C is transformed into an exact sequence of vector spaces. And second, faithful, which means that if you have a map from X to Y in the category C, and if TF from Tx to Ty is 0, if Tf is 0, then F is 0. So that gives me a complete characterization of a category of comodules as a category, an abelian category, together with a functor to the vector spaces, which has these two properties, exact and faithful. Now, once you have formulated things, it's routine to prove it. I will certainly not do the proof at the blackboard. What is important is that now of one half of the Tannakian categories. The rest is trivial. So very often it's stated the theorem of Saavedra is a complicated theorem, deep theorem. No, it's a trivial theorem, provided you take it. Well, I discussed with Delin, of course, Delin knew that. You can imagine that Delin knew that, but he never published it, but he knew it, of course. So now what do suppose now, take one more hypothesis. One more hypothesis. C, let's suppose that C is an abelian category with finite dimensional orbs. And suppose, moreover, we have a functor, I call it C, from C times C to C, which is bilinear. So the tensor product, an inner tensor product in the category C, which has the property you expect, associative, etc. And the more property you will put on this tensor product, the more property you will have on the coalgebra. Simply out of the existence of this functor, you get a multiplication in the category, in the coalgebra C. That means you get a map CT into CT tensor CT into CT. Routine. Just a composition of factors. Now, if you, any properties that you can assume on this tensor product translate immediately to a property of this map. For instance, if the tensor product is associative, this multiplication is associative. It's commutative in a proper sense, it's commutative, etc., etc. And also, it's important that this multiplication is a map of coalgebras. The tensor product of two coalgebras is defined, and this is a map of coalgebras, which means that the multiplication and the co-multiplication are compatible in the ordinary sense. Now, if you put more and more axioms, let's say, suppose that you have not only a tensor product, but a duality functor in C. The duality will give you an antipode on CT. And so what you have is that if you have, to summarize, if you have a tensor product which is associative, commutative with a duality, then you get a whole algebra. And now the end of the statement is the following. Now, if T is compatible with the tensor product in the category C, tensor product for vector spaces in K, then this equivalence that I defined, which was from the category C to the co-module over some, now becomes the representation, the equivalence of this category with the co-representation of some Hopf algebra. And everything is compatible. But once you have the tensor product comes at the end very, very easily. All my constructions were omitting the tensor product. So at the end, you get the result, which is known as Tannakian result. If you have a category with tensor product and suitable properties, if you have a functor which is exact, faithful, sorry, it's an abelian category, exact, faithful, incompatible with the tensor product, then it's an equivalence of the category as given with the category of all comodules over some Hopf algebra, co-representation of a Hopf algebra, and of course the compatibility respecting the tensor product, which is the important thing. So this is really Tannakian category. And in a functor which has all these properties called the fiber functor by the line, and Grothendieck-Teichmüller the line, and it comes out. So now just for, I will need a slight generalization of this. A slight generalization of this is the following. Well, and I did not say how to make the inverse. Well, the main point to the proof is to define the inverse functor. The inverse functor is some kind of tensor product. In any linear category, you can form the tensor product of an object in a category with a finite dimensional vector space. Well, if your vector space is simply Kn, it's a sum of n copies of your object. And that's what you need to go in the opposite direction. You need this construction, and you need, the point is that the inverse functor will be obtained by a co-tensor product of comodules, and we will have, the idea is as follows, that this, which is a crucial part of the co-algebra, is the image by T of something which is internal to C. This internal C, I mean, you just say, suppose that there is a duality in C, so it's an inverse tensor C x y tensor y. You have a duality. This is a vector space. These are two objects in the category C. So if you have a tensor product, if you have a suitable tensor product, okay. The point is that CT can be lifted to some object in the category, an end object in the category C. CT is an it's a co-algebra which is a inflating limit of finite dimensional co-algebra, as I've said, and then you can lift every such finite dimension co-algebra to an object in such a way it's a bit messy, but I will ignore that. Just I would say that I can define explicitly the inverse functor by some kind of tensor product, or rather co-tensor product. Okay, so now, well, I suppose it's a good time to make a stop, and let's see, I start again at 10 past. And then I will define for you the application, describe for you the application to geometry. And then I will, as I said, I recommend reading this paper by Delis. It is very informative and very well written.